Hello everyone, and welcome to the final topic of our safety and loss prevention module, and that is the topic of flammable substances. Now this lecture does have quite a bit of overlap with reactive chemicals and explosivity as well. However, it does have a few unique concepts that are essentially unique to flammability and combustion. Okay, so we're going to discuss the process of combustion and how it actually happens, and also methods to mitigate it, as well as concepts such as the flammability triangle, TNT equivalence, etc. Okay, so just to begin, okay, so this is the first slide of your lecture, and what we have here is a diagram illustrating flammability limits. Okay, so what actually makes a compound burn? What makes it combust? What makes it catch fire? Okay, so the first thing that you need to realize is that when something burns, it's actually first the gaseous phase of that compound that actually burns first. Okay, and as that gaseous compound burns, it generates enough heat to make other parts of the compound, perhaps the liquid part of the compound, vaporize and also catch fire. Okay, and that is how the combustion reaction actually propagates. Now we can think of, for example, silicon. Why doesn't silicon catch fire? Okay, so many of you have, you're essentially cooking with silicon utensils. Most modern utensils have silicon, so your spatulas, your baking spoons, they also have lots of silicon. And if you try and light it up, you take a lighter and you have a flame and you try and burn it, you'll find that it doesn't burn. It doesn't burn easily, even though it's silicon. It has lots of carbon in it. It should actually burn, but it doesn't. And this is because silicon is a solid. Well, yeah, it's kind of like rubber, but it's solid for all practical purposes. And just its melting point alone is 1400 degrees Celsius. Okay, so in order to burn that silicon, you would have to melt it. So the temperature has to be over 1400 degrees Celsius. And it also, not only must it melt, but it must vaporize. And it's that vapor that catches fire. Okay, so that is why silicon is actually very difficult to burn. Now we can look at, for example, another mixture such as, well, not a compound, but a mixture such as coal, your charcoal. Okay, so that's a mixture of hydrocarbons. It's very solid. However, if you try and light it up, it can catch fire. And this is because on a microscopic level, even though charcoal is solid, there are on a microscopic level hydrocarbons that are in the liquid state, perhaps as, some kind of vapor. And there are, on a microscopic level, compounds, parts of that charcoal that have already vaporized right at the surface of that charcoal. Okay, and if you try and ignite it, if you put an ignition source, let's say a match, a flame there, it's that gas that actually burns, and it increases the temperature so that more of that charcoal actually vaporizes and also burns as well. And that is how the combustion reaction propagates. Okay, now in some fuels it propagates very slowly, and in some fuels it propagates very vigorously. So we can compare, for example, charcoal with petroleum. Okay, petroleum is already in the liquid state and it has a very low flash point in comparison to charcoal, of course. And so it can burn quite vigorously. Okay, so in comparison to charcoal. And of course, they have different uses, as you know. So this is why we have, if this is your flammability curve here. And essentially, in order to burn something, you need a fuel and you need oxygen. Okay, that is, in general terms, you need fuel and you need oxygen. and that fuel has to go beyond the vapor pressure curve. Okay, so this is your vapor pressure curve here. Anything to the left, and you won't really have a flammable mixture. Okay, so you need some of that compound to actually cross this vapor pressure curve in order to get into this region here, which is your flammable mixture region. Now, as you increase the temperature, note that your temperature needs to, there is a minimum temperature. Sorry, there is a, yeah, as you increase your temperature, the range at which your mixture is actually flammable increases because your lower flammability limit decreases here and your upper flammability limit increases here. Now, what are flammability limits? They essentially are ratios between your fuel and your oxygen, or if it's burning in air, it's the ratio between your fuel and air. Now, you might think that, anything that's flammable will catch fire. However, there are certain cases where, even though something is known to be flammable, but if the concentration of fuel to oxygen is unfavorable, it won't really catch fire. Okay? So, as we increase temperature, the range of flammability increases. And the reason why we have this flammability range is because this is the region where the ratio between your fuel and your oxygen is actually good enough for all of that fuel to burn. Okay? Now, there are cases, so let's say above this flammable mixture, we have the upper flammability limit, and above this limit, the fuel concentration is so high relative to the amount of oxygen that there's essentially not enough oxygen for combustion to continue. So if you have to try and light a fuel under these conditions, perhaps you might get a spark or maybe 1 or 2 seconds of combustion, and after that it would just cease. The combustion won't occur. On the other hand, we have the lower flammability limit, and this is a case where the fuel concentration is so low relative to the amount of oxygen that your fuel molecules are actually quite highly dispersed. Okay? And because they are highly dispersed, even if you try with an ignition source, you try and light a match there, it would just be 1 second of burning and that's it. There won't be enough molecules to continue the combustion reaction. Remember, the combustion reaction is a propagating reaction. Okay, it's not just one sudden explosion. Okay, and then we get to a stage where the temperature can be high enough such that you get autoignition. Now, autoignition means that the compound will burn even if you don't have any match or any ignition source. Okay, so the temperature is high enough for the compound itself to actually burn. Okay, now in industry, how are fires and explosions prevented? They are prevented essentially through inherently safer design. This is why design safety or safety in design is a very important topic. Okay, so aspects of safer design include reduced inventories, substitution of compounds with less dangerous compounds, and trying as far as possible to operate as closely to atmospheric conditions. Okay, so reduced temperature and pressure. Okay, another mode of prevention is to prevent flammable mixtures from occurring. Okay, and as this diagram here illustrates, that is achieved through trying to control the fuel to air mixture, the fuel to air ratio. Okay, and the third preventive measure is to eliminate ignition sources. Okay, so in most cases, an ignition source is actually what causes a fire. And in industry, Most ignition sources are actually electrical sources. Okay, so live wires, hot cabling, they account for 23% of fire and explosion accidents. Okay, and thereafter it's followed by smoking, friction, overheated materials, etc. Okay, and then there are, of course, other ignition sources, mostly related to the reactivity of certain chemicals, for example, and various other random things. A hot kettle, a hot stove plate in the staff room, etc. That can all contribute to accidents. Okay, in terms of certain equipment, okay, so furnaces and boilers, they do of course naturally need to have combustion occurring, and safety is maintained typically through spacing and layout, appropriate spacing and layout of these pieces of equipment. Okay, flares as well. They're typically located very high up. You have a very tall chimney, and then you have the flare that's right above ground level. Okay, so manual labor, things like welding and tool work, is typically controlled using safety procedures. In terms of trying to prevent fires from spreading to other areas, we look at sewer design, use of dikes, trenches, and general good housekeeping of the plant. Okay, so presence of matches and lighters, so that's controlled through procedures, so simple rules such as no smoking in certain areas. Okay, hot surfaces as well, controlled using procedures and spacing. With electricity, of course, with our modern factories, we need electricity all over the plant. So we can't actually reduce that through spacing and avoidance and procedures. Well, we can use some procedures, but essentially electricity has to be in a number of places. And it's controlled typically through area classification. Okay, so just intelligent grouping of certain units and area classification. So you can classify an area as, high grounding, high electricity sources, or high energy usage areas, and you develop procedures accordingly. Okay, then you have grounding, inerting procedures, insulation, making use of the geometry, okay, as well as procedures. Now we'd focus on storage tanks and other pressure vessels. So even vessels like reactors, for example. The storage and use of chemicals and of course the avoidance of combustion of those chemicals and compounds is typically achieved through inerting and purging. Okay, so let's say if you have a fuel storage tank and that storage tank has a pressure rating, it can operate under pressure. So the space that's above the liquid, okay, so let's say if it's a liquid fuel and it's filled up in the storage tank, that air space above the fuel, instead of just having oxygen or normal atmospheric air containing oxygen, we can actually inert that air. Okay, and this is typically achieved through an inerting and purging cycle. Okay, so you add an inert gas such as, for example, nitrogen or helium. You add that gas to a combustible mixture to reduce the oxygen such that it's far below the limiting oxygen concentration. And we'll talk about this as we go along. So the inert gas is either nitrogen, it can also be carbon dioxide. Okay, steam is also sometimes used, but not that often. Okay, now there are certain ways of inerting, different ways. One way is the vacuum purge, where you firstly try and evacuate that space above the fuel and you replace it with inert. So you draw a vacuum firstly, and then you introduce an inert gas. Another method is to pressurize with inert. So you, instead of using vacuum, you pump inert under pressure, and thereafter you relieve that pressure, and hopefully some of the oxygen will come out in that relief cycle. Okay, now for vessels that are not pressure rated, that cannot withstand any kind of pressure changes, whether it be high pressure or vacuum pressure, they typically use a sweep purge process where you have an entry valve and an exit valve, and inert is just continuously pumped in, and over time that inert will push out some oxygen as well. So you do have inert coming in and going out, but you do also have some of the air with the oxygen also coming out. So over time the vessel gets filled with inert. Okay, then you have a siphon purge, which is typically used when you are first loading big tanks. So you fill that tank with liquid, you fill it completely with liquid, and then you drain the liquid. And as you drain that liquid, you fill that air pocket with nitrogen, okay, or any inert gas. Okay, and there are of course combination procedures such as combining the vacuum and pressure purge. Now looking at purging in a bit more detail. So we have vacuum purging. So you draw a vacuum. Okay, so let's say if this is your actual pressure, you draw a vacuum. And as you draw that vacuum, remember the air is actually getting sucked out of the vessel. The concentration of the oxygen in that air is not changing at all. However, the amount of moles of oxygen that are inside that vessel is actually decreasing. Okay, so you have that vacuum down to, so this is your vacuum pressure here. And then you inject an inert gas. At this point, your exit valve is closed, so your amount of moles of oxygen is not changing, but the concentration of oxygen in that air pocket is decreasing. Okay, and you repeat the cycle over and over again until you have a desired low oxygen concentration that's much lower than the limiting oxygen concentration. Okay, and we can actually calculate the concentration in terms of vapor mole fraction after so many purge cycles. Okay, so if that is your vapor mole fraction for any cycle, that's equal to your vapor mole fraction of your gas initially multiplied by the ratio of your vacuum pressure to your actual pressure, exponent J. Okay, so with pressure purging, again represented by a similar equation. So if this is your actual pressure, you start off by closing all exit valve and you pressurize. So you pump in inert. The moles of oxygen in your air pocket is not changing at all. However, the concentration is decreasing. And then when you close that inlet valve and you open the exit valve for the pressure to come back down, your oxygen concentration is not changing, but the amount of moles of oxygen is decreasing. It's getting let out through the exit valve. So you end up with less oxygen in that air pocket. Okay, so what do you choose? Vacuum purging or pressure purging? They have essentially their pros and cons. So pressure purging is faster because your pressure differentials are greater. Okay, so it's much more easier to pressurize something than to draw a vacuum. So for that reason, pressure purging can be a lot faster. However, if you're doing vacuum purging, you end up using a lot less inert gas. Okay, so remember, inert gas costs money. Okay, so we don't just have pure CO2 lying around or pure nitrogen lying around. Okay, so Vacuum purging uses a lot less inert gas than pressure purging. Combining the two can provide a number of benefits. So instead of only drawing a vacuum, you can draw a vacuum, and thereafter in your pressurizing cycle, instead of going back to the normal pressure, you can actually ramp up the pressure. Okay, and then there are of course other methods of inerting. So we've looked at sweep through purging. This does require large amounts of inert gas. Okay, so this is for equipment that are not rated for pressure. So you essentially don't have much choices. You have to just go through with sweep through purging. Okay, and then you have siphon purging, which is quite efficient for large storage vessels. You fill the vessel with a liquid, and as the liquid drains, you are filling that growing air pocket with inert gas. Okay, so in addition to just flammable chemicals, flammable liquids, we can also have dust explosions. Okay, so dust explosions are essentially combustion of dust particles, where the dust particles can be so fine such that the compound actually behaves like a gas, even though it is solid particles. Okay, so particles of 10 to 100 microns are vulnerable to this type of exposure. So let's say a silo containing flour or sugar, the particles can be so small that they can be very buoyant and they can essentially act like a gas. And if you burn or if you ignite that gas, then you can get a dust explosion occurring. Okay, now a dust explosion typically occurs like a deflagration reaction. Now, what is a deflagration? So let's say if we have all of our dust particles in the air and you have an ignition source, you light that ignition source, the particles that are very near that ignition source are the ones to catch fire first. But thereafter, how does it propagate? The heat from that combustion of those surrounding particles actually heats up more surrounding particles, and those particles catch fire, and so on and so on and so on. Okay, that's what a deflagration reaction is all about. So it's not just an instantaneous all of the gas burns, but it's a propagating reaction. Okay, and with certain, depending on what the fuel is, at times you can even see the propagation occurring. It's not that quick. Okay, now there are certain factors to, of course, achieve a dust explosion, a combustible dust explosion. The dust has to be of very tiny size, and of course, a certain concentration in the air. They can't be too dispersed in the air. You need an effective ignition source. You need the right amount of air. Okay, and you need dispersion of dust particles in sufficient quantity and concentration. If the concentration is too low, then even though you have certain particles burning, surrounding particles might be too far away to actually get the heat and catch fire. Okay, and the final and most important point, for an explosion, you need confinement of the dust cloud. Otherwise, you might simply get combustion of the cloud, but you won't get explosion, because remember, an explosion happens through the buildup of pressure. You need pressure buildup, generation of gases that are trapped, the pressure builds up, then a rupture or an explosion occurs. Okay, so properties which influence the explosion hazard: the minimum ignition energy, flammability limits, the deflagration index, as well as the explosion pressure and ease of dispersion in the air. Okay, so in terms of your minimum ignition energy, that depends on the particle size, the composition, temperature, presence of moisture, turbulence, the amount of oxygen, and whatever test method you are trying to use. In terms of your deflagration index, KST, it's used to quantify the explosion violence for a specific dust, and it's needed when specifying explosion relief vents. Okay, so when we are working with dust particles that are very tiny, and if you need to keep them in a silo, such as food products such as flour, for example, you need to actually measure this deflagration index, and it's this index that can suggest how violent a potential explosion can be. And if you know how violent a potential explosion can be, then you can design your silo to have certain relief valves to prevent an all-out rupture of that silo. Okay, so numerically speaking, your deflagration index is the maximum rate of pressure rise. Okay, the maximum rate of pressure rise, of pressure increase for a deflagration of a dust-air mixture in a 1 meter cube spherical vessel. Okay, and at an established level of turbulence and ignition energy. Okay, in terms of flammability and explosion in general, there are certain chemicals that, well, most chemicals that are combustible, they need oxygen and they burn in an oxygen-rich atmosphere. However, there are certain mixtures that don't need oxygen at all to burn. Okay, so for example, if you interact chlorine with hydrocarbons, you can get a combustion occurring. Okay, even though there's no oxygen, instead it's using chlorine. Okay, so you can in fact test this out if you want to buy some HTH. Remember, HTH has a lot of chlorine in it, your pool chlorine, that HTH powder, and you can add it to brake fluid. Brake fluid is essentially a mixture of glycols and alcohols, so essentially hydrocarbons. And you can simply just pour that powder into the brake fluid and watch. It will take a couple of seconds before it begins to burn without oxygen. Okay, so typical ignition sources, we've been through this here as well. And this diagram here essentially just categorizes all of the different types of explosions. Okay, so there are chemical explosions and physical explosions. The chemical explosions essentially need a reaction. Okay, whereas a physical explosion is mostly concerning a phase change, and that phase change results in high pressure. Okay, so things like rapid phase transition, vessel rupture. BLEVE is it's just an acronym. So boiling liquid expanding vapor explosion. So essentially, if you have a boiling liquid, that liquid is turning into its gaseous state. It requires more volume. If it doesn't get more volume, it's going to build up in pressure and your vessel will rupture. Okay, so that's what BLEVE is about. Okay, your chemical explosions, either you can have uniform reactions or propagating reactions. Okay, now uniform reactions, they are homogeneous, so thermal or runaway reactions can lead to an explosion, so things like polymerization. And then you have your propagating reactions, such as your deflagrations and detonation. Okay, so what's the difference between detonation and deflagration? Okay, so when a cloud is ignited, a cloud of vapor or a cloud of dust particles, if it's ignited, the flame can propagate in one of two ways. Okay, one is detonation and one is deflagration. The difference is, of course, the speed. And I'm not talking about this just in relative terms, but it's also the speed of the reaction relative to the speed of sound. Okay, so for a detonation, upon ignition, the reaction, it propagates faster than the speed of sound. And because it's propagating faster than the speed of sound, it drives a certain shock wave. Okay, so it drives the shock front immediately before it. And that is why a detonation can be highly violent. So let's say if you have here, looking at your distances, a house at this point here can be experiencing ambient pressure, and as this shock wave moves, suddenly it goes from ambient pressure to a sudden high pressure spike. Okay, and that can essentially destroy your house. Okay, then you have a deflagration, and in a deflagration, your reaction propagates at a certain speed, and that speed is typically less than the speed of sound. Okay, so you have this pressure front that's being driven by the reaction, but the pressure front is moving at the speed of sound, and the reaction is moving slower than the speed of sound. Okay, and as a result, you have a more gradual pressure buildup rather than a sudden experience of very high pressure. Okay, so another point to make here. So in the case of explosives, they typically prefer a detonation type reaction because detonation is more, I would say it's more efficient and more optimized in terms of actually harnessing that amount of pressure. Okay, because remember, the purpose of an explosive is to actually destroy something. So if you're designing an explosive, it's going to require detonation, and that releases a large amount of pressure that's enough to destroy whatever you want to destroy. With the deflagration, however, it's energy inefficient. Okay, so you have this gradual pressure buildup. It's often quite noisy, and there's a lot of energy dispersion. So this is not something that you typically want in an explosive. Okay, so this is typically more of a hazard that you want to avoid, whereas detonation, of course, does have certain uses. Okay, so we've also looked at this slide before in the previous lecture. So an explosion is a violent self-reaction or decomposition. It can be initiated either through heat, by ignition, or by mechanical shock. Okay, in terms of high explosives, you want essentially a detonation type reaction. In your explosive, you typically have a mechanical or electrical initiation of that reaction, and thereafter what causes the damage is actually the shock wave. Okay, then you have your pyrotechnics, which burn and produce heat, smoke, light, and also noise, and propellants, which burn and produce heat and gas to drive engines. Okay, now in terms of measuring explosive power, we can look at any type of fuel or any source of an explosion, and we can rate it in terms of a TNT equivalence method. Okay, so what is TNT? TNT is trinitrotoluene. Okay, it was developed in the 1900s. It's been used as an explosive since 1902, and the reason why TNT is so popular as an explosive is because it's actually quite stable. It's actually quite difficult to detonate TNT. Okay, so it can be used in a variety of cases. There's very low risk of accidental explosion. Okay, so that is why they use TNT in a variety of military applications and also in civilian applications. So the destruction of a building to construct a new one. Its use in mining as well to break up rocks. Okay, so they also use TNT. Okay, so you essentially have good control. Now, in terms of detonating, the detonation heat of 1 ton of TNT is typically 1,000 kilocalories. Sorry, for a ton, sorry, it's 4.6 gigajoules per ton. Okay, and we can convert that into per kg. It's 1,000 kilocalories per kg, or 4.652 megajoules per kg as well. Okay, now if we know our heat released, okay, so that's 4,652 kilojoule per kg, then we can essentially compare any other explosion to an equivalent mass of TNT. So let's say if you want to measure the explosive power of nitroglycerine, or even something a lot simpler such as the combustion of flour in a silo. Okay, so we can measure that in terms of TNT equivalents. Okay, so we can do that using this equation here. So you can measure the energy of explosion or the heat of combustion. Let's say if you have that. Heat of combustion is quite easy to obtain. If you know what the reaction is, then you can essentially use heats of formation and look at the combustion reaction, and you can calculate the heat of combustion using the heats of formation. And MC, that is your mass of your fuel that you are using. Delta H TNT, that's of course the energy of detonation of TNT per kg. This E over here is the efficiency factor. Okay, so it's up to 0.5 for a gas confined in a pressure vessel, and it's 0.03 to 0.1 for a vapor cloud. Okay, now an explosion can be quite inefficient. Okay, remember that an explosion is not really it's not a well-controlled event. If something explodes, the energy is dispersed 360 degrees around it. Okay, so essentially in a spherical direction, and most of the time you don't really want that. So there's a lot of energy that's actually wasted, and there's of course other energy being wasted in the form of light and in the form of sound, which you don't really want. So all of that amounts to a low efficiency factor. Okay, so for TNT, it's typically an efficiency of 0.5, which is as good as it gets. And you can also achieve that with a gas confined in a pressure vessel, particularly in a spherical pressure vessel. You'd get an efficiency factor of 0.5. But looking at a vapor cloud, so let's say just any cloud of dust particles, either in the atmosphere or in a very large cylindrical tank, the efficiency can drop very low to the point where you have more energy being dispersed as sound and as light rather than an actual shock wave. Okay, so this is the equation. And once we've achieved this, once we've attained our information from this equation, the benefit of using TNT equivalents is that it's quite highly studied, right? So TNT is quite a highly studied explosive, and for any kilogram or for any ton of TNT, the effect of that explosion is very well studied. So remember that if you have an explosion, the force or the pressure of that explosion is highest the closer you are to the explosive. Okay, as you go further and further and further away, the pressure wave essentially disperses. Okay, so as it goes to your actual point in question. Okay, so that includes estimating. So we can use your TNT equivalents to estimate overpressure from any distance. Okay, so you use this equation here. Your scale distance is equal to the actual distance divided by your equivalent mass of TNT to the power 0.33. Okay, so if you know your scaled distance, then you can find your overpressure. And then you can compare it to a table. So let's say, for example, let's say if you are at a point near the explosion, where if the explosion occurs, it will give you at your distance an overpressure of 0.4. Now that overpressure of 0.4 is so great that it can actually demolish most houses. Okay, but if you are further away, perhaps the overpressure will drop to a lot lower. It will destroy maybe half of the houses. Houses further away, perhaps you'd get your doors and windows shattered, but the structure will still be there. Okay, an overpressure of 2 bar, your actual ground would be destroyed, the ground on which your house stands. So your house, the foundation of the house, even that ground, it will all be blasted away at an overpressure of 2 bar. What's its effect on trees? If there are trees experiencing an overpressure of 0.8 bar, either the entire tree would be destroyed or the branches will be broken off, and also utility poles as well. And overpressure also affects, of course, people. Okay, so depending on what the overpressure is here, so let's say an overpressure experience less than 0.07, although it can shatter doors and windows, your casualty likelihood is not very high. Okay, so it's not going to affect someone's health that significantly. However, as you increase that overpressure, your casualty probability increases as well. Okay, so looking at an example, let's say we have a cloud containing 1 ton of propane. Okay, and it ignites, it leads to a vapor cloud explosion, and they want us to estimate the overpressure at a distance of 150 meters away from that explosion. Okay, so they've given us the heat of combustion of propane, and of course we know the heat of detonation. So for 1 ton of propane, we can substitute it in here, and we can get the equivalent ton of TNT. Okay, and we can already compare. So 1 ton of propane, that's equivalent to 455 kilograms of TNT. We can take this and apply it to a scaled distance. So we get the scaled distance. And thereafter, we go to our correlation for TNT overpressure. And at a distance of 19.5, okay, so that's essentially somewhere here, we can get our overpressure. Okay, so the overpressure is 0.045 bars. So 0.045, you're going to get at least 50% of your windows shattering if you are located in a house that's just 150 meters away. Okay, so other concepts, we've looked at spontaneous combustion, water-sensitive materials, and oxidizing agents. We've looked at that in the previous lecture. Okay, looking at explosive chemicals. Your explosion is essentially a self-reaction or a decomposition generally. It's initiated either by an ignition source of extreme heat or mechanical shock. And your explosive materials are categorized by the speed at which they expand. So materials that detonate, the speed of that reaction, propagation, is higher than the speed of sound. That makes it a high explosive. Materials that deflagrate, they are low explosives. Okay, explosions are essentially, once it's initiated, you get quite a spontaneous chemical reaction, large negative enthalpy change, and large positive entropy change. It, of course, creates a lot of chaos, a lot of disorder. And large quantities of gases are released, and large amount of energy that was originally stored in chemical bonds are released. Most commercial explosives are typically organic compounds, and most of them typically contain nitrogenous functional groups. So your NO2, NO3, N3, nitrogen double bonds as well. Okay, so another example, in addition to your trinitrotoluene, is your nitroglycerin. This actually has a lot higher explosion energy than TNT. However, it's also a lot more unstable, so its uses are quite limited. Okay, now lastly, we can actually study the flammability of chemicals using a flammability triangle. Okay, so any typical environment, you typically have a fuel, and that fuel is burning in air, and air contains mostly oxygen and nitrogen. Okay, so you have your fuel-air mixture represented by this flammability triangle, and there is an example in the tutorial where you use this flammability triangle to actually establish whether a mixture will be flammable or not. Now, relevant information. Okay, so let's say we have a fuel. Firstly, how do you read this triangle? It's often quite difficult. Many students forget how to read the triangle. So if this is your fuel here, your fuel line, the line for actually reading of your composition of your fuel is located here. So that's 0, 20, 40, 60, etc. And essentially your lines are horizontal. Okay, so that's looking at your fuel composition measurements. You use horizontal lines and you use the scale over here. Your oxygen measurements are essentially on this side of the triangle. So that's your 10, 20, 40, 60, etc. The actual composition is read off using these diagonal lines moving downwards here. Okay. And your nitrogen composition is read here at the base of the triangle. Anywhere inside the triangle, you're moving up these diagonal lines. Okay, so that's essentially how you read this ternary diagram or this flammability triangle. Now looking at your actual compositions, so if this point here represents 100% fuel, then this entire baseline here actually represents 0% fuel. So along this line, you will have only oxygen and nitrogen. So let's start from a consideration of having just air and no fuel. You'd start off with the point over here. So that is your 79% nitrogen, 21% oxygen, and 0% fuel. And as you introduce a fuel into this mix, so let's say if we're looking at a closed container, it's originally full of air. But now let's say you are injecting a fuel such as propane into that container. As you inject more and more fuel, your composition of your fuel increases according to this line here. Okay, now let's say if you are in a position to evacuate all oxygen and nitrogen and have just 100% fuel in your container, then that would be the point over there. So any point along this line here is representative of your fuel-air mixture. Okay, so that's your fuel-air line, which you simply draw by connecting your point from here at 79% to that pinnacle over here. Okay, so that's one relevant line. Okay, then you have the stoichiometric line. Remember that your fuel will burn in oxygen. Okay, it's only the oxygen that's actually reacting with the fuel. The nitrogen doesn't play much of a part. So let's say if, for example, your fuel is reacting with the oxygen, let's say in the case if there was only fuel and oxygen and no nitrogen at all. So that would represent the base of this triangle here. And at this point here, this is essentially the stoichiometric value or the stoichiometric composition of oxygen, which would burn all of the moles of fuel. Okay, so that's that point there. And as we increase, if we are looking at air, and as we increase the amount of nitrogen, theoretically to 100%, we end up with that pinnacle there. So we can quite easily draw a stoichiometric line from the stoichiometric oxygen to 100% nitrogen, and that's your stoichiometric line. Okay, and associated with your condition of having 0% nitrogen, if you have just fuel and oxygen, there is of course an upper limit of pure oxygen and a lower limit of pure oxygen. So below which there'll be no combustion here, and above over here there'll be no combustion occurring. So that is your upper and lower flammability limit if there was no nitrogen present. Okay, this is also called the upper oxygen limit and the lower oxygen limit. Along your air line over here, this point here is known as your upper flammability limit. So this takes into account if your fuel is burning in the presence of air. That is your upper flammability limit composition. And here would be your lower flammability limit. Now if you have all of these points, you can draw up a flammability zone. The final point here is known as your minimum oxygen concentration, or it's also called LOC, the limiting oxygen concentration. Okay, so as you can see, remember you're reading your oxygen off by going up here, so that's your oxygen. So if you go any lower, there'll be too little oxygen to actually burn all of that fuel and to have combustion occurring. So if you know these relevant points, you can quite accurately draw up a flammability zone and determine whether a fuel can be flammable in a variety of situations. Okay, so this is how you read the triangle. It is of course best if I could actually draw the triangle and show it to you by hand, but unfortunately that's not the case for now, so we're going to have to make do with the slides. But this is your flammability diagram, and this is how you read it, so I've gone through that before. Okay, your air line represents all combinations of your fuel plus the air. Okay, now your stoichiometry, remember that your fuel plus oxygen will give you products. Most of those products are CO2, H2O, but we're not really interested in that. What we are interested in is the stoichiometric amount of oxygen required to react to that fuel. So once we have that stoichiometric value here, converting it into a composition, that's Z over 1 plus Z multiplied by 100, and you'd get your point here in percentage. In terms of your other points, if you know what your stoichiometric amount is, you can calculate your stoichiometric concentration in pure oxygen and also your concentration in air. And if you have these two CST values, you can calculate your LFL and your UFL in air as well as if you only had oxygen. Okay, so that's how your flammability limits are essentially estimated. This is essentially a correlation. It's fine for most uses. In certain cases, it's a bit too optimistic, and it's not so conservative as it should be. Okay, your limiting oxygen concentration can also be calculated using your Z, your stoichiometric value multiplied by LFL. It's typically 8 to 10% for most fuels. Okay, so a good example, so methane, we can actually perform all the calculations. So if we are given the values here for pure oxygen and in air, finding our stoichiometric value, so that's 66.7, and we can actually draw up our triangle and establish the flammability zone. And we can use this flammability zone and look at a variety of situations to establish whether a mixture would be flammable or not. Okay, so there is a very good tutorial question on this in tutorial 4, which would hopefully be uploaded by now. And yeah, so please attempt it. And if you have any questions concerning either this lecture or the tutorial, please feel free to drop me an email. Okay, so that's the end of this lecture. Thank you.